Good afternoon to everyone. My name is saketh. I am from EC department. Today my topic is a hybrid wired wireless deterministic network for smart grid. First of all, introduction. The fourth industrial revolution, Industry 4.0, is experiencing high speed development. It uses sophisticated information and communication technologies for intelligent networking for machines and processors. In Industry 4.0, time crucial and applications executes tasks with hard real-time constraints where given deadline must be satisfying along with strict constraints on reliabilities, latency and jitters. One of the key attributes of Industry 4.0 is power grid, which is rapidly evolving to smart grid. For instance, the next generation of smart grid networking technologies need to provide high, reliable, and low latency synchrophasor communications. Measurement units are deployed in large number of monitors in the health of the power grid in real time, hence requiring a secure and reliable communication infrastructures. Wide deterministic network for smart grid. With the proliferation of the Ethernet based network in sustained systems, timing protocols such as a network time protocol, IR, IRIBB, IRIGB, and 1 pulse per second may not be sufficient to achieve timing accuracy less than 1 second, as well performing reliability greater than 99.99% and the latency less than 10 millisecond at the same time, improving the quality of the synchrophasor measurements, especially for a sustained automation system, would require a secure and deterministic communication infrastructure with much greater timing precision. In particular, with the widening PMU installations in massive number of for wide area monitoring, demands for high communication bandwidth connecting continues to grow. To comply with such strength requirements, we consider a deterministic time sensitive network, namely Ethernet, Ethernet, time triggered Ethernet cable for achieving contact latency and minimum latency. This is mainly because TTE compensates transmission jitter that is introduced during the traffic propagation and propagation of the switches. Furthermore, to remotely control sensor devices such as intelligent electronic devices, it is important to utilize a wireless technology with high reliabilities and low delay. Therefore, the TTE based network architecture should be able to provide a wireless solution for interconnection critical and non-critical non-critical data wherever the wide access is not available. Under this condition, it is important to utilize a wireless technology guarantee that can guarantee reliability, accuracy, and low delay information exchanges. Therefore, an integration of wired and wireless network that can connectively coordinate timing and synchronization with the TTE backbone network is a key technology challenge. Wireless deterministic network for smart grid. Currently, these are limited wireless options available that can match the high precision timing or reliability of the TTE network. For instance, there is an ongoing standard activity to offer a new generation of wireless local area network referred to as Wi-Fi 7. The future Wi-Fi 7 will be based on the IEEE 802.11b amendment, which will build upon 892.11ax, focusing on LAN indoor and outdoor operation with stationary and predestined speeds. More importantly, it aims to provide time sensitivity capabilities to enable high reliability and low latency in the 2.4 and 5 and 6 gigahertz license expect spectrum bands. A timing measurement protocol similar to the PTP can be used to achieve high precision lock synchronization between a primary node and its secondary node. Wireless deterministic network for a smart grid. While Wi-Fi 7 is still it is not in infancy, 5G URLLC will provide the most reliable and the wide available wireless communication. Bear in mind that among the three scenario application scenarios covered by the 5G network, we consider the URLLC for our wireless expansion. Obviously, this would require designing and highly synchronization area infrastructure while TTE as the main bus can provide wireless access via URLLC. URLLC is designed to support the strengthened latency and reliability requirement of mission critical applications. This includes providing time synchronization across the network orthogonally frequency division multiple access reservation to reduce latency scheduled across for better control of the channel access and link adaptation. Such important features makes 5G URLLC highly suitable for integration with TTE for time sensitivity communications. TTE based on the AS6802 standards, which has been developed for the integrated system that safely related application. However, implementing AS6802 based high precision time synchronization in URLLC requires the adoption in installation of TTE controls in the all component of the network. PTP aided 5G URLLC wireless network. PTP is defined as in order to provide sub-microsecond network time synchronization with high accuracy, which makes it suitable for time sensitive critical applications. DP is defined as the wireless propagation delay from the primary to the second, and DSP is the wireless propagation delay from secondary to the primary. PTP message using the end-to-end delay measurement mechanism exchanged between the primary and secondary clock for a synchronization are depicted in figure 1. The PTP primary clock sends synchronization message once every synchronizational interval. The sync message contains the clock identification information, the specified accuracy of the primary clock based on the current reference source, as well as an estimated timestamp T1 of the sync message transmission time. Since the estimated timestamp T1 in the sync message may not be accurate enough, the primary clock will send a follow-up message with a more precise value of the timestamp T1 to secondary clock. As soon as the sync message is received, the secondary clock will stamp the reception time to T2 using own clock. The difference between the sync message departed and the timestamps T1 and the arrival timestamp is T2. It is combination of the secondary clocks offset from the primary clock and the wireless channel propagation delay. The secondary clock then sends back the delay request message to the primary clock and stores the departure time with the timestamp T3. When the primary clock receives the delay request message, it sends the delay response message to secondary clock, which contains the timestamp of the T4 of the reception of the time corresponding to the delay request message. Propagation delay formula is T4 minus T3 plus T2 minus T1 is entirely divided by 2. The composition of the propagation delay is based on the assumption that the primary to the secondary and secondary to the propagation delay are equal. User equipment with high mobility will experience the asymmetric wireless link, which is caused by the rapidly changing distances. However, in URLLC and end-to-end delay between base station, This figure 2 is describe the hybrid wire and wireless deterministic communication network for time critical applications. Generally, there is a limited delay asymmetric in implied URLLC wireless network. Under the above conditions, the clock offset between the primary clock and the secondary clock is expressed as the often value is equal to T2 minus T1 minus propagation delay. By exchanging these synchronization messages, the end device would be able to accurately measure offset and then update their clocks accordingly in the order to achieve synchronization with primary clock. PDP, which was originally proposed for wide network, has been successfully used for time critical wireless applications such as URLLC. It should not meet restrict latency requirement. Smart grid and industrial automation are two important use cases scenarios of URL LLC. In both scenario, high reliability, low latency, and strictly bounded jitter would be essential as time synchronization in instinctive read, time coordinate, and interaction moving among devices. Proposed hybrid deterministic network. The precision of the synchronization depends on the clock drift of each local clock. At synchronization matters the integration cycle. Smallest integration cycle results in smallest offset, hence the higher precision synchronization. In this process the TTE integration cycle is offset the same values as the PTP synchronization intervals to avoid any inconsistencies as shown in figure 2. In the TTT domain, the TTE switch is configured as a CM while its associated GNB and other end systems are configured as SMS. While the associated UEs function as the PTP secondary clocks. After synchronization, TTE switches and GNB's primary exchange PTP message with the associated UG secondary to distribute the global time. Conclusion. In this presentation, I presented a hybrid wide wireless deterministic network architecture that integrates the TTE wired backbone network with PTP aided 5G URLLC wireless subnetwork. Specifically, the high-speed TTE is considered to achieve high bandwidth deterministic communication, while 5G URL is employed to obtain near deterministic wireless communication access to the in order to remotely control you control PMUs and other critical sensory devices. Thank you to high precision time synchronizations and links reservations mechanism to both TTE and PTP aided URLs that provided that processed hybrid network in shown into the capable to the supporting time critical service with the low latency and the very low jitter. This guarantees reliabilities for the industry 4.0 as demonstrated by the robust performance of the proposed hybrid network. Thank you.